Okay, so today I'm going to be presenting on the cloud model. I do apologize, I know my voice sounds a little electric-y. I'm new to all these different programs that I'm trying on my computer right now, so eventually I'll get better at this, but for now, this will have to do. Okay, also I've added a table of index to help make navigating this, all the sides for Unit 2 a little bit easier. So, today we're going to talk about the cloud model, also known as Aufbau's hotel. That's the analogy that I use to explain the cloud model. The reason I'm doing this is because some of you guys were not present this day. Others of you could just use a bit of a refresher. I know it's a really confusing idea, so this is what we're going to work on today. Okay, so according to the planetary model, which we just learned about before the cloud model, we learned that there's some kind of a nucleus. Get into drawing. Okay, so first we had the planetary model. In the planetary model, we had some sort of a nucleus right here, right? Where we had all of our protons and neutrons. Protons were positively charged, the neutrons were neutrally charged. The neutrons help hold these protons together. Then, according to the planetary model, we have all of these neat little rings around the nucleus. So all of these neat little rings. I have terrible handwriting, or terrible art skills, especially on a computer, so I apologize if these circles look nothing at all like circles. Okay, so according to the planetary model, we've got some nucleus in the center, and these little orbits of electrons around it. And in this very first orbit, we'll have 2 electrons that move in neat little circles. In the second orbit, we have 8 electrons that are moving in nice little circles. In the third orbit, we have another 8. Okay. And then if we were to add another orbit, we then have 18. And the numbers keep getting higher. We don't really know why. And obviously we can have less than that, but that's like the max we can hold in any single orbit. And we learned about how electrons could jump between energy levels or between these different orbits, these different rings. But we never really understood why any of this was happening. But it's a nice way to be able to visualize the atom, and so that's part of why we use it. Thus, it's not altogether terribly inaccurate. However, today we're going to learn about a different model. Today we're going to learn about something called the cloud model. In the cloud model, instead of having orbits, we have orbitals. And yeah, so we're going to look at a model for the atom where the electrons are being viewed in 3-dimensional space. So, a couple of things. First, in the cloud model, we still have a nucleus. So we still have our protons and neutrons right here in the center. But now, we're actually taking a closer look at what these electrons are actually doing. Thanks to Schrodinger, we wound up finding out that electrons don't move in these neat little orbits around the atom. Turns out these electrons have way too much energy for that. These electrons are actually zipping around like crazy in space. And in fact, we can never predict where an electron will be at any point in time. However, we can find out the odds of it being in a general location. And so that's why we create these clouds, these probability clouds. So it turns out that all these atoms have different clouds where chances are the electrons will be located somewhere within that cloud. So that's kind of what I'm trying to show here. So here we've got a bunch of different electrons in these 2 different S clouds, or sphere clouds. So it's forming a sphere around the around the nucleus, and the electrons are being located somewhere within that sphere. If this doesn't make a ton of sense, that's okay. We'll learn more about this later on. But basically, the important thing to know is that we can't know where an electron is at any given point in time. So instead, we just try to figure out the general places where it's probably at. Much like how, if you don't know where your sibling is, you might say, oh, well, my brother's home, saying they're somewhere within the entire house, but you don't know which room exactly. That's pretty much what we're doing here with the cloud model. Okay, so, if for some reason you're taking notes on this video, taking notes is great, so please feel free to take notes. These are the main questions that we're really hoping to try to answer with this presentation. So you have access to the slides. I'm not going to linger on the slide. If you need to, you can pause the video to take notes as I'm going through this. Okay, so the cloud model is a super advanced, super complicated idea. However, you guys can totally get this. So I have faith in you guys. If you still have questions after this video, shoot me an email. I check my email pretty regularly, and I'll get back to you and try to explain or clarify whatever we have confusion about. That being said, because the cloud model is such a complicated idea, I'm going to use an analogy. My analogy is called Aufbau's Hotel. This is Mr. Aufbau. This is his very peculiar hotel. This hotel starts small on the bottom and gets big at the top. Okay, so it's going to be really important that we learn a couple rules. Since this is Aufbau's hotel, it's important that we learn Aufbau's rule. So his rule, put in common everyday English, would be that nobody can move on to a new room until the old room is full. Basically, he's kind of stingy. So he wants to make sure that you completely fill each room, left to right, bottom to top, from the hotel, before you move on to the next room. Okay, so if we were to look inside of the hotel, this is what we would wind up saying. We have 7 different floors. These 7 different floors are called correlate to the energy levels of an atom. It also correlates to the 7 periods of the periodic table. So if we were to look over at the periodic table, there we go, we would see that the periodic table has 7 periods, 1 through 7. And so it turns out those 7 periods correlate to Aufbau's hotel. This is basically just a periodic table flipped upside down. Now you might be wondering to yourself, okay, well what about all these elements down here? Where are they at? Well, it turns out this isn't actually what the periodic table looks like. If we were to look at the periodic table in its fullness, we would find that it actually looks like this. So all the atoms do fit within these 7 periods, or within these 7 rows. However, this is really awkward and long to look at, and it's just a pain, a bit of a nuisance. So we usually choose to look at this more condensed version of the periodic table. Okay, so we've got our 7 floors, which represent the 7 energy shells. Or if we were to look at the planetary model, these would be 7 different rings. Okay, so in addition to that, each of these rooms has a certain name. So if you went into this hotel and you wound up getting placed in a S room, that would mean you'd wind up in a room that only has 1 bed. This is, like the ideal room that you'd want to wind up in. Whereas if you wind up in a room with 3 beds, you're in one of the P rooms. Or if you're in a room with 5 beds, it's a D room. Or if you're in a room with 7 beds, you're in one of the F rooms. So this also correlates to the periodic table. So it turns out on the periodic table, we divide it up into different blocks. You'll see here this version of the periodic table has them color-coded. So we have our S block, which are these guys right here. We have our P block, which are all these guys over here. We have our D block, which are those guys. And our F block, which are all these guys at the bottom that kind of get cut out. So whenever you're looking at a condensed version of the periodic table, they're basically just cutting the F block out and sticking it at the bottom. Okay. So, those are the different rooms. Every room is either an S, a P, a D, or an F. Okay. So, Mr. Aufbau reminds us that these beds are twin beds. That means that we can fit up to 2 atoms or up to 2 electrons in each bed. So, let's look back at the periodic table in light of this. So this first bed can hold 2 atoms or 2 electrons. Well, if we look at the periodic table, you'll see that on our first energy level, the first floor of the hotel, we have 2 atoms, hydrogen, which has 1 electron, and helium that has 2 electrons. So it shouldn't surprise us that those will both go here. Likewise, hydrogen and helium are both in the s block. So on the first energy floor, or on the first floor, we only have 2 atoms, hydrogen and helium. You'll notice there's no P's up here for energy level 1, just hydrogen and helium, and they would exist on this first floor. So if we first walked into the hotel, we'd find hydrogen and helium here, because they've got 1 and 2 electrons, respectively. Then if we went upstairs, we go to room 2S. It's named 2S because we're on the second energy level, or on the second floor of the hotel. When we walk into the second floor, the first S room, that's 2S, we're going to find lithium and beryllium, because they have 3 and 4 electrons respectively. Also, neat thing about p-table, this actually tells you where the electrons are located. So beryllium, it's got its first 2 electrons on that first floor, and then it has its second 2 electrons on the second floor. That's what this is showing us. So these 2 guys they're once again in the s block. So lithium and beryllium would be located right here. And if we walked through to the next room on the second floor, we come to 2p. 2p has 3 beds. Each bed can fit up to 2 electrons or 2 atoms. And so this means we could fit 6 electrons or 6 atoms in here. So on the second energy level, we just walked out of S. So now we're over to the p subshell. Well, fun fact, the periodic table has 6 atoms in the p subshell, or 6 atoms wide. So in that room, we'll find boron, carbon, nitrogen, oxygen, fluorine, and neon. Likewise, you can still see this is telling you how many electrons are in each floor. So it's got 2 electrons in your 1s, 2 electrons in your 2s, and then the rest of the 6 electrons are in the 2p. So all of these guys would be located in this second room. Then if we were to go up again, we now go to the third floor, which we remember correlates to the third period of the periodic table, and we're entering the S room. The S room has just 1 bed, holds 2 electrons or 2 elements, so this would be sodium and magnesium. Obviously, the next place we'll go will be to a P room, which will have 3 beds with space for 6 atoms. So we can hopefully see how this correlates to the periodic table. Likewise, you'll notice the D rooms have 5 beds, which can hold 10 atoms. So if you take a moment and count this, you'll see there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 atoms wide. The D block is 10 atoms wide. And if we were to count the F block, we'd see it's got 14 atoms wide. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This guy right here is actually part of the D block. It just got shifted down. Okay, so it's 14 wide, which makes sense because the F block up here has 7 beds and can hold 14 atoms. I do apologize if I'm throwing too much at you or if I'm going a little too fast here. So please, if you have questions, write them down, pause the video, write down the question or whatever is causing confusion so you can send me an email and I can hopefully clarify this a little bit. Okay. So, we covered Aufbau's rule. Aufbau says we have to start by filling up this bed from the bottom and work our way up left to right. So if we had 1 electron, it would wind up in this first bed. If we added a second electron, he points out the beds are twin beds, so we wind up putting 2 electrons in this first bed. Get this? Okay, cool. So if we were drawing electrons, if we had 1 electron, our first electron would go here, second electron would go here. If we had lithium, which has 3 electrons, we'd have 1 electron here, 1 here, and its third electron would go here. If we had beryllium, it would have 4 electrons, 1, 2, 3, and then the 4th one would go here. If we had boron, we'd have 5 electrons, so it'd have those first 4 electrons, and the 5th one would go here. If we did carbon, which has 6 electrons, we'd have 1, 2, 3, 4, 5, but then the 6th electron would go here. And this is because of something called Hund's rule. So, basically, these electrons are all negatively charged, and so they want to be as far away from each other as possible. So this leads, oops, I need to get out of pointer so I can move. Okay, so basically, these electrons want social distance. They don't want to be really close to each other, because negative charges will push against each other, much like how the protons pushed against each other and needed neutrons to hold them together. Similarly, these electrons don't want to be very close together, so they're going to try to social distance. So they won't share a bed unless they absolutely have to. And when they do share a bed, they're going to sniff their feet, which means basically they'll be facing opposite directions. So if you had 4 electrons, 3 beds, this is how they would spread out. You have 3 sleeping in the bed normally, and then the 4th guy would be forced to share a bed, and so he'd face the opposite direction. That would be Hund's rule. Okay, so you can kind of see here, this is how we would fill up the beds using these electrons. Okay, so hopefully this part makes a bit of sense. I know it's a really strange analogy. I know it's super bizarre. Just try to bear with me here. Okay, so another thing. Core electrons and valence electrons. It turns out that most of the properties of an atom, something that determines how an atom acts, is dependent on its valence electrons. Go away. Okay, so it turns out these valence electrons determine the most about how an atom winds up acting. These core electrons, I mean, they're helpful because they help determine the size of the atom, how large the atom's going to be, but they don't do a lot to determine how that atom acts. A lot of how the atom will wind up acting will be based on how many valence electrons it has. So it turns out this is how the periodic table is also set up. So the periodic table is also set up to reflect this. So everybody here in this first family all has one valence electron, or one outside electron. So we can think of this much like an apple with an apple peel. You've got the inside of the apple being the core electrons that you can't see, and then you have the valence electrons being the peel of the apple. That's what everybody comes in contact with. And so when we think of an apple, we think of the peel because that's what we see. So likewise with these atoms, we really care about the valence electrons. So hydrogen has one valence electron. Lithium has one valence electron. Sodium has one valence electron. Potassium has one valence electron, and so forth. So we can go through all of these guys, and they all have one valence electron here at the bottom. All of these other electrons are core electrons. So these guys would all be underneath it. But the valence electron is the only one we really care about because that determines how francium is going to act. And this causes all of these atoms to act pretty similarly. So, the periodic table is set up to reflect this. So, our first family, these guys all have one valence electron. Then we come to our second family, these guys all have 2 valence electrons. We skip over the F block and the D block and come to this family. And this family all has 3 valence electrons. As we can see, 3 valence electrons. All these other guys are core electrons. Come to this family, we're up to 4 valence electrons, as you can see. When we come to this family, the pnictogen, they've all got 5 valence electrons. Then we come to the chalogen family, they all have 6 valence electrons. Come to the halogen family, we've got 7 valence electrons. And lastly, we come to the noble gases, and all of the noble gases have 8 valence electrons. So that's how the periodic table is set up. You might be wondering, what about all these DNF subshells? Well, they're all just a little bit weird. We'll talk about them later. They're kind of the rebels. They don't follow the rules very well. Okay. So, now I'm going to kind of break down the analogy a little bit more. Hopefully we could kind of figure out how to figure out where atoms from the periodic table would be located on this hotel. If you haven't, I really strongly encourage you to take a break, pause the video, and choose an atom and try to figure out where it would wind up on this. So here's how we would do that. Let's say we did fluorine. I encourage you all to stop and do this on your own, and then press play and check and see how this is going. Okay, so if we're trying to find out where fluorine would be located, first thing we're going to do is notice how many electrons it has. Fluorine has 9 electrons. So, when we put it in this hotel, we're going to follow Aufbau's rule and Hund's rule. Okay. So Aufbau's rule says we have to start by filling up the bottom first. So we'll have one guy laying like so, and the other guy, according to Hund's rule, says you don't want to stay in the same bed unless you absolutely have to, and then we'll be facing the opposite direction. So the second guy will be laying like that. So we've got 9 electrons. We'll just work our way up, left to right, bottom to top, following Aufbau's rule. So that's 1, 2, 3, 4, 5, 6, 7. You might notice I put them in different beds first. That's because I'm following Hund's rule. 8, 9. Had 9 valence electrons. We have 9 electrons. So I laid them all out. We have 7 valence electrons, 7 in this top shell, and 2 in the bottom. And so this adds up nicely. And that's what it would look like. So hopefully all of this makes sense so far. If not, please email me so I can try to clear this up a little bit. Okay. So now I'm going to try to break down the analogy a little bit. So the cloud model is broken up into 4 main subsections. We've got energy levels. Energy levels were represented in the planetary model as these different hoops, as these different rings. Or in the hotel, the energy levels were each of the different floors of the periodic table. And likewise, in the periodic table, energy level is organized by periods. So we've got 7 different energy levels or 7 different periods. And the energy level helps determine the size of the atom. And so this makes sense. We remember that in the planetary model, if we had a hydrogen atom and we heated it up, that electron would jump from one ring to a higher ring, thus making the atom larger. Or if we added a lot more electrons to an atom, it's going to get bigger because we're filling up more rings. So the energy level determines the size. Also, when we represent the energy level with a letter, we choose the letter N. That's why in my hotel, I have all of these as being N. So N1 is the first energy level. N2 is the second energy level. Okay, then we have subshells or sublevels. The subshells and sublevels determine the shape that this atom forms, or the shape of the clouds that these electrons wind up in. And for this, we can think back to the cloud model that you guys actually built in class. You'll remember that we talked about how the S subshell was the sphere that you made, the P subshells. I can actually show you guys images. So we made something in class that looked like this. Go away. Okay, so we've got our S subshells being spheres, or P subshells look something like this. Some people said peanuts or Pringles, or I think somebody mentioned it looking like an infinity. So these are the P subshells. Yeah, go back. Okay. So our subshells look like this. We've got our S subshell, our P subshells, our D subshells, which look a little bit like donuts, and then lastly our F subshells that look like flowers. So the subshells help us determine the shape that these electron clouds form, these clouds of probability. Then we have orbitals. Every single subshell has a different number of orbitals. So much like how in the hotel there was a different number of beds, right? If we had 1 bed in a room, it was a S room. Or if we had 3 beds in a room, it was a P room. Well, similarly, this is because every subshell has a certain number of orbitals. So if we're in a subshell S, we only have 1 orbital. If we're in a subshell P, we have 3 orbitals. Subshell D has 5. Subshell F has 7. If we were to keep going larger, we just keep adding 2. So next would be G with 9, H with 11, and so forth. It's a pretty simple pattern. Why we chose SP, D, and F initially, that's a long story. But basically, just remember that each subshell correlates to a certain number of orbitals. So S subshell has only one orbital, P subshell has 3, D subshell has 5, and F subshell has 7. And all of these guys are stacked on top of each other. Okay, so what's up with the orbitals? Well, every orbital can hold 2 electrons. So that means if we have an S subshell with just one orbital, we've got 2 electrons. If we have a P subshell with 3 orbitals, then we have 6 electrons. If we have a D subshell with 5, 5 times 2 is 10. F subshell with 7, 7 times 2 is 14. And each of these orbitals are going to be separated by something called a node. A node would be like a no-go zone, where these electrons can't go. They always have to be somewhere within one of these clouds. They can't be between the clouds. And fun fact, if you use p-table, you can actually see what these different electron clouds look like. Not necessarily super easy to visualize, but you can see these guys a little bit. So radium's probably a really good example of this. You can see the different subshells. It's kind of like taking a chunk out so you can see it. And in between each of these different S subshells, there would be a node where the electrons can't go. Okay, now you might be wondering to yourselves, okay, that's nice, but why can we only have 2 electrons in an orbital? Well, let's talk about that real quickly. It turns out every single electron has something called a magnetic spin. So these electrons, if we remember, are moving at the speed of lightning, because lightning is actually just a bunch of electrons moving around. So we've got essentially lightning moving around in a subatomic space, something so tiny you can't even see it with a microscope. So these electrons are zipping around here like crazy, so fast we can't even tell where they're at. That's why we have electron clouds of probability. So these things are zipping around like crazy. But that's still not enough. They still have to exert some movement. So it turns out that they also wind up spinning as they zip around within this cloud. And so these electrons are zipping around, wind up spinning one of 2 directions. If they're spinning one way, we call it positive. If it's spinning the opposite way, we call it negative. It's a little bit arbitrary how we're doing this. But we're just going to assume that they first go positive and then negative, because we need some way of talking about how these electrons are spinning. And so it turns out, in class I actually demonstrated this with magnets, where I showed you that by spinning one magnet to the left like this, we cause the other magnet spin the opposite direction. But I can't really do that here. But basically, there are only 2 spins available. Because there are only 2 spins available, we can only have 2 electrons in each orbit. Okay, so I'm about done. I've tried to make this quick. I do apologize. I know it's been hard. So last thing. DNF subshells are exempt from a lot of things. So you might have noticed earlier, or I mentioned earlier, that the D and F subshells didn't follow the valence electrons very well. Like here we've got manganese with 2, and niobium with 1 valence electron, and it's just kind of random how these guys act. Turns out there's a reason for this. It's called electron shielding. Basically, by the time we're getting to atoms that are this big, we have so many different electrons that we're dealing with that they shield the electrons from the positive attraction of the nucleus. So we'll remember that like charges repel, right? Let me see if I can draw this. Come on. Okay. So in our little model here, we have some positively charged nucleus, and then we've got these clouds of electrons around it. So some sphere of electrons for S subshell. So we've got 2 electrons here, and the reason these electrons don't just wander off into, way out here is because they're being attracted by the nucleus. So this positive charge is keeping the electrons nearby. And then when we add more electrons, they have to be further away because these electrons in the first subshell are actually pushing against them. So these electrons are telling those electrons, go away, we don't want you here. But the nucleus is still attracting these electrons. But by the time we get to the D subshells, we've got so many levels. Sorry, I lost my pen for a moment. Okay, we've got so many different levels of subshells. We've got our two S's, we've got a P subshell that looks something like this, and the X, Y, and Z axis. And we've got a whole another S subshell, an even larger P subshell. So we've got all of these electrons that are pushing against the new electrons that we're adding. That causes some of these new electrons that we add to be displaced. So even though the nucleus is still pulling on these electrons, all these other electrons are pushing against the electron. They're all trying to get it to go somewhere else. And so this results in the new electrons being displaced sometimes. And so for this reason, the D and F subshells sometimes don't follow all the rules very well. Primarily, they tend to not follow Aufbau's rule very well. And this whole thing is called electron shielding because the electrons are acting like a shield. So hopefully I was able to clear this up a little bit. Hopefully this was helpful. If you have questions, please don't hesitate to contact me and ask them. And yeah, thank you for your attention.